Today's lab are all
Feel like
about
this,
skeletal muscle.
Again,
Right?
seeing
So there are two parts to the lab today. You have the EMG, which you're going to do on the biopack. So you're going to have to pick a volunteer from your group that's going to be hooked up to the electrodes again, and that you're going to be able to measure the grip strength on. After that, we do have two Connect labs where you're going to see kind of the same thing, but a little bit different. Right? In this case, you'll be looking at grip strength, and then eventually time to fatigue. How long does it take for the muscle to fatigue? Now we'll talk about fatigue here in a second. You definitely want to know that definition. Right? Absolutely, positively make sure you know what fatigue, muscle fatigue means. Right? So that is the plan. Just like last time when we did this, we'll start with the biopack and then move on to the Connect labs. That way when you're done with these, you're pretty much good to go. Right? So as far as the objectives, one, make sure you understand what a motor unit is. Make sure you understand what a motor unit is. Understand what a motor unit is. Understand what a motor unit is. Two, know what an EMG is and what it can be used for. Know what an EMG is and what it can be used for. Know what an EMG is and what it can be used for. Three, know what a myogram is. Know what a myogram is. And be able to draw and describe a basic myogram. Know what a myogram is and be able to draw and describe a basic myogram. Know what a myogram is and be able to draw and describe a basic myogram. Four, understand what motor unit recruitment is. Understand what motor unit recruitment is. And be able to interpret the results. And be able to interpret the results of that lab, of that Connect lab. So understand what motor unit recruitment is and be able to interpret the results of that Connect lab. The last one, be able to define muscle fatigue. Be able to define muscle fatigue. Be able to define muscle fatigue. And interpret the results of the muscle fatigue lab. Be able to define muscle fatigue and interpret the results of the muscle fatigue lab. So those are going to be the objectives. Please think about those objectives as you guys go through the lab, and then definitely make sure you can meet those objectives by the end of the lab, or by the end of the study period that you have for this lab. Right? So as far as our skeletal muscle lab goes, as the name implies, we are going to be dealing with skeletal muscles. Now recall that skeletal muscle tissue is not the only type of muscle tissue found in the body. Besides skeletal muscle, we also have cardiac muscle and we have smooth muscle. Unlike cardiac and smooth muscle though, skeletal muscle is a voluntary type of muscle tissue. What does that mean?
Conscious movement.
Yeah, we can consciously control when these muscles work, when the muscles contract. So anytime you produce a movement, you are consciously controlling those skeletal muscles, and you're making them work. And as they work and eventually pull on the bones that they're attached to, that's what produces the movement that you're trying to make. So true or false, skeletal muscles are involuntary. False, right? Skeletal muscles are voluntary. Now, does that mean that all of our skeletal muscle contractions are voluntary? Or do you suppose some happen involuntarily?
Involuntary.
Some will happen involuntarily, right? Some we are not aware of, right? For example, when we breathe, we're not constantly thinking about our diaphragm contracting, right? We're not making the diaphragm contract. When we sit upright or stand upright, the erector spinae muscles of the back that are holding you upright, they're just contracting, right? Once you make that decision, they're just doing that, right? So not all of them will be completely voluntary.
So does a reflex count as involuntary?
That is completely involuntary, right? So reflexes are involuntary, right? We don't decide to do that, right? Remember, that's an action that'll happen without the brain's involvement. Right? Most of them are going to be spinal reflexes, so involuntary, even though it involves skeletal muscle. So please note that. Now, as far as how skeletal muscles work, in order for a skeletal muscle to contract, it does have to receive the electrical impulse from a motor neuron. So a motor neuron is a neuron that will typically synapse with a skeletal muscle and control its action. These motor neurons typically secrete or will secrete acetylcholine to excite that skeletal muscle cell. How many people have gone through chapter 12? That's a good one. That's a big one. All right, if you've gone through chapter 12 and you've gone through the sarcomere and you've gone through the end plate potential, right? The end plate potential is kind of what sets off that skeletal muscle. So this is where the neuron will secrete acetylcholine onto a skeletal muscle cell. As that acetylcholine diffuses across the synapse, it eventually binds to cholinergic receptors on that skeletal muscle cell. Once acetylcholine binds to those receptors, it's going to open non-specific channels on the surface of that skeletal muscle cell. Now, if we're opening non-specific ion channels on the surface of this skeletal muscle cell, what's going to move in? Any ideas? Already? Sodium. Why sodium? Not so much. Why would it be sodium? Why would sodium be diffusing in? Yeah, there's always a high concentration of sodium outside of our cells, right? So once we open those non-specific channels, what does non-specific mean?
Anything goes.
Anything can go through as long as it'll fit. And since sodium is the most abundant ion out there, what's it going to do once those channels open? It's just going to diffuse through those channels. And it goes into this cell. Once it goes into this cell, Mia, what does it make the cell? More positive or more negative? A bunch of sodium is coming in. More positive, right? So where all of this sodium is coming into that cell, we start to see a change from negative to positive. This change from negative to positive at this specific site is called the end plate potential. Right? Now, you've taken anatomy and you remember, what does a skeletal muscle cell look like?
It's like a tube.
Long tube. Right? It's a long tube. Right? Which means this motor neuron is only coming into contact at one specific site, and that's the motor end plate. We have the rest of the cell now that we have to worry about. But think about what we just said, right? We allowed a bunch of sodium to come in here at the motor end plate. This particular part of the cell now is becoming very, very positive. Here's the amazing part about these cells. This is the part that I just absolutely love about these cells, right? Once you start going beyond this motor end plate on the plasma membrane, instead of having specific channels that are bound to a neurotransmitter to open it, now as we move away from this motor end plate, we have voltage-gated ion channels. Nobody thought that was the name? Brandon, your hat didn't fly up here? Voltage-gated ion channels. Think about the name, voltage-gated ion channel. Madison, voltage-gated ion channel. What do we need to change in order to open that channel, based on the name? an electrical signal, right? We need to change the voltage. Did we have a change in voltage here when we initially opened those non-specific channels?
Mm-hmm.
Yeah, if sodium came in at the motor end plate, there was a change in voltage there. So now if that's a voltage gated channel that's adjacent to this area, is it going to experience that change in voltage? Absolutely. So what's it going to do? It's going to open. And guess what happens on the other side of the motor end plate? Any voltage gated channels that are there are also going to experience that change, and they're going to open. So now as these voltage gated channels open, what's going to happen there?
Chain reaction.
More sodium comes in, right, which makes now this larger area even more positive. What's going to happen to adjacent voltage gated channels that are near this area? They're going to open. And what happens? More sodium comes in. So now you're starting to depolarize the entire cell. And once we depolarize that entire cell and it has an action potential, that action potential will now move deep into that cell. And then if you've gone through the lecture, you probably know what's going to happen next. Right? If not, when you hear the lecture, take it from there. Right? I will tell you though, once that action potential moves deep, a bunch of calcium is released into the cell, and that's what causes the sliding filament mechanism to work. Right? And now you have a muscle contraction. So without this initial change in voltage, right, without this end plate potential, can we excite the entire cell? Not a chance. Right? So please consider that. Right? We have to have a motor neuron stimulating this cell to produce the contraction. This is going to take us then to what a motor unit is. Now when we think about an entire skeletal muscle, so take a quick look at your neighbor. Right?
If someone looks.
Specifically look at their biceps muscles, if you can. Don't be shy, look at their biceps. Right?
Stop.
Go ahead, roll up your sleeves if you can.
Stop it right now.
How many people got a ticket to the show? The good show, right? You've never heard that joke, huh? I'm sorry, that was the first time you did. My bad, that was a bad joke. So, look at that biceps brachii muscle. Is that made up of a single cell or multiple cells? Multiple cells, right? Multiple cells. So in order for that muscle to completely work and to generate its maximum force, there are going to have to be multiple motor neurons stimulating all of these cells. Now, that means that usually our skeletal muscles won't just have one motor neuron controlling the entire muscle. There are going to be multiple motor neurons. So let's say you guys are all individual muscle cells, except for Mia and Francesca and me. We're motor neurons. Everyone else is a skeletal muscle cell that's a part of this biceps brachii muscle. I'm in charge of synapsing with all of these skeletal muscle cells. Mia's in charge of synapsing with all of those skeletal muscle cells. And Francesca's in charge of synapsing with all of those skeletal muscle cells. Right? Now, depending on the amount of force that we need to generate, do you suppose all of these cells are going to be working at once?
He's gonna do it.
Have a pen. Right? I'm going to curl this pen. Right? So I'm going to physically make this muscle work.
Oh no.
Right? Was that difficult? Why not? It's very light. So do you suppose the entire biceps brachii muscle was working at that point in time? No. Which means not every single cell in that muscle is being stimulated at that point in time. I'm only stimulating the cells that are necessary to be able to produce this movement. Which means I'm only stimulating a few cells. Considering that and considering the example we said, this is what a motor unit is, right? A motor unit is a motor neuron and all of the skeletal muscle cells that it synapses with. Which means a motor unit is a motor neuron and all of the cells that it synapses with. So this would be one motor unit, that's another motor unit, and this is another motor unit. So by definition, Kelly, what's a motor unit? A motor neuron and all of these cells, skeletal muscle cells that it controls. Right? So motor neurons, Mia, Francesca, get ready. Right? When the motor neuron fires, what's going to happen to all of the cells that it controls?
You better get hyped.
You guys all better get excited here. Anna, get ready.
Excited.
And as long as I'm firing, these cells are contracting. Right? And we're generating that much tension. Right? It's a little bit heavier.
Holy
Right?
crap.
Can you do
A little heavier here, right? So now, in order for me to move this, do you think I might require more motor units?
Un poquito más.
Possibly, right? So now, get ready.
Holy crap, what's happening?
So now, are we generating more force? Yeah, because we have more cells working, right? I don't know what's happening to that one, right? Keep in mind, once the motor neuron stops firing, what do all those cells have to do? They have to stop as well, right? There's nothing else stimulating them, right? So please note that. And now if I try to do this, right, it's just going to be even heavier.
Oh my.
Yes. Right? So to do this, I need even more motor units. Right? Get ready, Mia. What's going on here? Right? As soon as the neurons fire, the cells have to go. I don't know what's happening with this cell right here. As soon as that motor neuron transmits those neurotransmitters, the cells have to work. Right? Remember, it's the way that skeletal muscles work is kind of the way that an action potential works. All or none. Right? So once it goes, everything has to work. Right? So, as needed, we can recruit more motor neurons, or more motor units to generate more force or more tension based on what we're doing. Right? What if I try to lift this table? Is there any tension there? You better believe it. Right? So am I using a bunch of motor units right now? I'm trying to, right? But nothing is happening, right? Because I can't generate that much force to overcome this load. Right? So I might have recruited all my motor units, but I'm not doing anything, right? Because I just can't generate that much force. Right? Yeah.
So when people say like when you have an intense adrenaline rush and you can like lift a car or something, how does that?
So in those cases,
hormone
you
that?
do end up using the majority of your motor units, right? And you do end up using the majority of your skeletal muscle cells, right? But that's that kind of situation, right, where it's like a life and death thing, right? In those cases, a lot of times they end up kind of damaging their skeletal muscles because it's just too much force, right? We're not typically intended to produce that much force, right? But that is a product of that situation, right, and the rush of adrenaline. Right? There are people, though, that in general can activate more motor units than us regular folks. Right? There was a show, Stanley's Superhumans, back in the day when all the Marvel movies started coming out. And there was a guy that they had on the show that would just rip a phone book in half. You guys know what a phone book is? Yeah. The Yellow Pages, right? No? It's a big, giant book with a bunch of phone numbers in it. That's where all the information was back in the day before cell phones, right? So this guy would grab the phone book and he would just tear it in half, right? So they hooked him up to a machine like we're gonna do today. They did a bunch of EMGs on him, and in general, on average, he had more motor units working than the average person. So on average, he was able to generate more force than the average person because of, again, motor unit recruitment. So as needed, in order for our skeletal muscles to generate more force, do we need to activate more motor units?
Yes.
Yes.
When you build muscle, do you get more motor units, or how does that work?
No, so for the most part, our muscle tissues, once we make that muscle or that organ, those are the cells we have. What tends to happen is the cells get bigger. Right? As they get bigger, inside of the cells you have more sarcomeres, you produce more contractile proteins, which means you can end up generating more force. Right? But typically you don't make new cells.
So
Right?
you're like 1% number of motor units.
That's it. Right? That's it. And if you damage any of them, then that's a pretty much done. This becomes really important, particularly in the heart. Right? If you have a heart attack, that tissue doesn't repair itself. Right? So please know that, right? The cells just get bigger. And internally, you do make more sarcomeres, and that's what causes the generation of more force. So please make sure you understand what a motor unit is, and again, what motor unit recruitment is going to be. Right? Now, in our first lab today, we are going to be doing an electromyogram. Right? An electromyogram. An electromyogram is essentially a graphical representation of the muscle contraction. So you can see the force that's being generated here. As far as what we're measuring, right? We're measuring force and active motor units. And the basic one that we're going to do here in the lab, we're really just measuring force. But in the in the Connect labs, you will be able to see active motor units. Right? So know that in an EMG, depending on how it's being done, you can measure both the force and you can see how many motor units are active. So in our EMG lab today, we are going to be looking at the differences in force that are generated with your dominant hand versus your non-dominant hand. So whoever the volunteer is going to be squeezing these little things, the little headbands that we used last time. Right? So you'll start with kind of a gentle squeeze, and you progressively get stronger and stronger and stronger. You'll be able to see the differences in the amount of force generated on that EMG. And then you'll compare that to your weaker arm. Which one do you suppose is going to generate more force? Should be the dominant. But sometimes it's hard for people to control their non-dominant arm. Like when you tell them to gently squeeze, they go all the way. Because they can't gauge that because it's the non-dominant arm. So sometimes that can cause differences in this. So we'll see what we end up getting. But generally speaking, it should be your dominant arm. Right? So please note that. Now, as part of this lab, we're also going to be able to hear the actual muscle contraction. Right? So before you completely close it out, we do have headphones. They're up here. I'll pass them out to each individual group. And once you collected your data, you can then plug the headphones in and listen to a muscle contraction. Again, if you've listened to the lecture, or if you know what the sliding filament mechanism is, consider that when you hear the sound. Right? It kind of sounds the way that it works. So we'll be able to listen to that. Otherwise, here's a very basic myogram. So for test purposes, this is the one I want you to consider. Right? So again, very basic, just showing you a few things here. Notice at the very top, these represent the electrical impulses that are stimulating this particular skeletal muscle cell. So usually at the top, you see the electrical impulse. Now, in these myograms, especially when you're doing EMG, usually whoever the controller is generating these impulses, right? So they can send these electrical impulses to stimulate the muscle. Right? So as we see this would be one electrical impulse. Now notice the electrical impulse actually happens before the muscle contraction. So this little area here before the muscle contraction, when this impulse hits, this is known as the latent period. The latent period. The latent period is the time that it takes for all of the little cellular mechanisms that have to happen in order for the muscle to contract to happen. Right? So this is all the calcium coming in, all of the myosin heads binding to the actin filaments, and then the actual contractions happening. Right? So will a muscle contraction be instantaneous? Meaning as soon as you stimulate, will the muscle contract? No, there's a small lag here, and this is milliseconds, right? But there's still a lag. What is that lag period called? Latent period. The latent period. All the cellular mechanisms are happening here. And then you actually see the contraction. So in this particular contraction, as the force increases, this is what's known as a twitch. You ever heard the term muscle twitch? Twitch just means that the muscle's contracting. Right? So in our simple twitch here, this is our contraction. As the force increases, we now have a contraction. So here we generate that much force, and then what happens? relaxes, right? Notice there's no other electrical impulse here. So we stimulated, it contracted, and now it's relaxing. And it's going back down to the baseline. Again, this first thing that we're seeing here is a simple twitch. It's a contraction immediately followed by a relaxation. And what happens before the contraction? Again, what is that time period called? Latent period. Contraction, relaxation. The next cycle, notice what we see. We have our stimulation, we have our simple twitch. We see the contraction, and then as we see it going to relaxation, boom. Notice what we do now. We re-stimulate the muscle. So as we re-stimulate, notice now what happens to force. Force increases. So now we're able to generate more force upon that second stimulation. Based on this, is there a lot of time between those stimuli? No. So depending on how quick you re-stimulate the muscle, it is possible for us to continue to generate more force. The reason for this happens at the cellular level. Earlier I mentioned that you're going to need calcium to contract these muscle cells, to make them contract. So as we go into our relaxation phase, right, that calcium is starting to get pumped back into the sarcoplasmic reticulum. But what if you re-stimulate right away and you make all these mechanisms kind of restart again? You suppose at this point we're going to continue to pump that calcium into the sarcoplasmic reticulum, or are we just going to leave it there now because even more is going to come out now? We're going to leave it there, right? So since we already have some calcium there from the previous contraction, as we re-stimulate and release even more calcium, this allows the cells to produce more cross bridges. More cross bridges means more force. So this is why we're able to generate more force here, because of all of the kind of residual calcium that was left over from the first simple twitch. Does that make sense? If you haven't listened to the lecture, it probably doesn't, but when you do, I'll come back to this. And now notice as we get to the third phase that's drawn here, what's happening as far as stimulations? Just multiple quick stimulations, which means we're just going to continue to see summation, 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 until eventually we reach the peak force that that muscle cell can generate. This last phase then is known as tetanus. Tetanus, which means this is the maximum amount of force that muscle cell can generate. No matter how much more we stimulate there, we're not going to be able to produce more force. So please consider that tetanus, right? Any questions on that? Yeah.
The whole thing with how you said there's like residual calcium from like a previous contraction. Is that why like for sports people would like warm up because it activates the muscle and has
Absolutely. Absolutely. You warm up, you get the muscles working, right? You get more blood flowing to the muscles, which means you get more oxygen for ATP production, but you also start getting some of this happening. So it's definitely important to warm up before you start doing any type of physical, like really physical strenuous activity. Right? Please consider this. With this, I also want you to kind of think beyond this now. Let's say you are hooked up to an electrode, right? And whoever the controller is gives you a voltage. If nothing happens, why do you suppose that's the case? If I, let's say, give you a voltage of 0.1 millivolts and nothing happens to the muscle.
Stimulus isn't strong enough.
It's not strong enough. It's not strong enough to produce anything, any response by the muscle. So will we see anything on the myogram? No. Will we see any increase in force? No. If I then turn up the voltage to, let's say, 0.2 millivolts now, and you do see a response, what does that mean?
Adequate stimuli.
That's the adequate stimulus, right? That's the minimum amount of stimulus needed to get the muscle to actually produce a contraction. Now, if I continue to increase voltage, what do you suppose will happen to force? It continues to increase. Right? Now, eventually, if we're just stimulating that particular muscle and we continue to increase force, you suppose at some point we're going to reach a voltage where we've reached the maximum force that muscle can generate. Probably, So if we continue to increase the voltage beyond that, will we generate any more force? All right, once we reach the max, and that's what we're stimulating, you can increase the voltage all you want. There are just no more cross links that we can produce to generate any more force. Right? So please kind of keep that in mind. Otherwise, again, for the EMG lab, you will need a volunteer, and you will need, again, the person controlling the biopack. So, as usual with these, please follow the instructions as far as how you're going to place the electrodes. It's going to go on the right forearm today, and then eventually on the left forearm, depending on which arm you start with. And then you'll fill in the data table and interpret those results. Right? So with your summary, I just need the last few pages. Don't include the entire package. Just need the data table and the questions. And you're going to do questions D through J. So just this page. I don't even need the second page. Okay. Once you're done with that, from there you move on to the Connect labs. Where in this Connect lab, we are going to look at motor unit recruitment. Motor unit recruitment. Where you're going to see how motor units are recruited as, again, you increase voltage. So in this particular biogram, you will be able to see the increase in force. You're going to measure that with amplitude. But you're going to also see the increase in voltage, which is also measured with amplitude. And then you'll be able to see the amount of time, and the computer will measure the frequency of those action potentials for you. So as you initially start, you're going to start with a small voltage, which means that you're going to generate a lot of force here. Now, eventually you'll go to a very large voltage, which means what's going to happen then? Even more force. So you'll start with a little bit of force, and the amount of force will increase. As that happens, what do you suppose is happening to the number of motor units that are being used? It's increasing as well. Right? So true or false? The more motor units are functioning, the less force you're going to produce.
False.
False. If you have more motor units working, you're going to generate more force. So think about that next time you're lifting weights or you're working out. If the weights get heavier, you're going to have to generate more force. From there, you guys will move to the time to fatigue lab. So the setup is going to be very similar here, but unlike this one where you start with a small amount of force and work your way up to a high amount of force, here you're going to start with maximum force. And you're going to try to hold that maximum force for as long as you can. Now, if I'm sitting here with a 50-pound dumbbell and I'm curling it like this, am I going to be able to hold it like this for the rest of the lab? No, what's going to start to happen?
Fatigue.
Right? I'm going to start to fatigue, and that weight is going to start to drop. Right? By definition, muscle fatigue is the time that it takes for us to get to 50% of the maximum strength initially generated. Time to fatigue, or fatigue by definition, is the time that it takes for us to get to 50% of the force that we initially started with. So just random numbers here. If I'm generating 100 Newton meters of force, when I get to 50 Newton meters of force, true or false, the muscle is fatigued? True, right? I'm at 50%, right? So whatever time it takes for me to get to 50%, the maximum force generated initially, that's muscle fatigue. Considering that, is the muscle still working technically?
Yes.
Yeah, the muscle's still working. So when muscles are fatigued, they are still technically working, right? Are they generating the maximum amount of force at that point in time? Not a chance. Right? At that point in time, by definition, how much force are they generating? 50% of what we originally started with. So please make sure you guys know that definition. So in this lab, you're just going to be looking at the amount of time that it takes for you to get to that 50% point. So you'll be measuring the force, and you'll be looking at how many active motor units you have from start to finish. And you only go for, I think it's like 1 minute and 15 seconds. So as usual with the Connect labs, These will be very quick. As usual with these, when you get done, call me over so that I can ask you some questions. Once you're done with that, you're good to go. Any questions, comments, or concerns? All right, so go ahead and start getting into your groups. Start deciding who's going to be the volunteer.
Bro,
We have the electrodes up here.
and it's like, bro, I just got a
I
fresh
will
ass
combine
haircut.
with the
Look at this. Do you not remember, gang?
you're going to be squeezing and the headphones.
It's only our forearm.
Otherwise,
really?
go ahead
Yeah,
and
that's what he
start
said.
it.
That's only our phone? That's some bullshit, bro. That's why it's been recording you the whole time, man.
You guys are